Okay. So, are there any questions?
We have now time for kickoff.
What?
We got now time for kickoff.
Probably not. I mean, what is it, like in 30 minutes? Oh. Now, which one are you talking about? Oh, I don't know. Doesn't it start at 6:30? I have no idea. I mean, if it's 7:30, then you just might. Because we were having some technical issues with the earlier class. Any other questions? No? Ready to learn? Not ready? Oh. What? Do you have any questions? Okay. All right, well, so we're in section 3.3. We're going to talk about quadratic functions and some good things that they can provide. And we'll start section 3.4, and we'll finish section 3.4 on Wednesday, and 3.5 as well. So, quadratic functions. So, the definition of a quadratic function is f of x equals ax squared plus bx plus c, where a is not 0. So you have a square term. That's the big message here. And the graph of a quadratic function, no matter what it is, no matter what the function is, as long as it's quadratic, is going to be a parabola. So no matter what a function is, it's going to come out as a parabola. It will come out as a normal parabola, looking something like that, opens up, if the leading coefficient is positive. If a is greater than 0, the parabola will open up. Okay? And if a is less than 0, and that's what we talked about last week, all the transformations, if a is less than 0, the parabola will open down, so it looks something like that. Positions, depending on the function, but in general, it'll be an upside down parabola if a is less than 0. Okay? Now this point on the parabola, we call that point a vertex. This is a vertex of a parabola. And just by looking at the graph, if you look at the first graph, does this function have a maximum point or the minimum point? Minimum. You agree with that? Just by the way it looks. And the opposite is for the other one. It'll have a maximum point. So we can actually predict whether our function will have a minimum point or maximum point just by looking at the sign in front of the x squared. So if you have a positive number in front of x squared, you're going to end up with the minimum value. And if you have a negative sign in front of x squared, you'll end up with the maximum value. And it would be really nice if we had a tool to find that vertex. Because I know how much you all enjoyed a few homework assignments ago when you had to heavily use the graphing utility in order to find those maximum minimums. Yeah, wouldn't that be nice if we had a way of avoiding the use of graphing calculator to do that? And we can do it with the quadratic functions. But just as a quick example, if I write something like this on the board, for example, f of x equals negative 3x squared plus 1, let's say, that is a quadratic function. Do you agree with that? All you see is the x squared, and then the rest doesn't really matter. It's a quadratic polynomial. Does it have a maximum or a minimum? Okay, minimum, maximum, y. Right, because you have a negative in front of x squared, so it falls into the second category. So it's an the graph will be an upside down parabola. Okay, so it will have a maximum point. So this one has a maximum value. But in order to find the maximum value, we'll just have to find the vertex of that parabola. And that's what we're going to spend some time today trying to figure that out. So here's the big message. To find the max or min of a quadratic function, we just have to find the vertex of that function. So that's what we're going to spend on this first half of the class, is the ways to find the vertex of a parabola. Okay? So we understand how to shift the parabola. We spent some time last week to talk about when you shift to the left, when you shift to the right, up, down, when you flip, and things like that, right? So if I give you a problem, for example, if I give you this function, f of x equals negative 3 times x minus 4 squared plus 1. Can you quickly sketch a graph of that function? How would we do that? How would we go about sketching a graph of that function? Oh. So go to the right, flip it, and then go up 1, right? So it looks something like that. I'm not, the x-intercepts, I'm being very careless about that. The negative in front. So the negative in front flips the graph over the x-axis. So here's the vertex. Do we know the location of that vertex? What is it? 4, 1. So this function obtains the maximum value of 1 when x equals 4. Okay? So x equals 4 will give you the highest point on the graph of that function. And that highest point happened to be 1. Does that make sense? So maximum value of the function is 1, and that occurs when x equals 4. So pretty straightforward, right? If we understand all the shifts and the function is given in this form, then the life is really good. So this general form, f of x equals a times x minus h squared plus k, we like that form because it will tell us exactly where the vertex is. It will tell us exactly whether it's a maximum or a minimum. So the location of the vertex is going to be hk. So it shifts, h units horizontally and k units vertically. And the sign of a will determine whether we have a maximum or a minimum. If a is positive, we'll have a minimum. If a is negative, we'll have a maximum. Okay? So we like this form. This is good. Right? Good at that. Life is nice and easy. Let's try it again. If I give you this example, g of x equals 2 times x plus 1 squared minus 4. I know the vertex without doing any much work, right? What is the vertex? Negative 1, negative 4. Because in order to grab this parabola, you have to shift 1 unit to the left and 4 units down. Will that be a maximum or a minimum? Minimum. So actually this will be the minimum. Happy? Yeah. So that's the opposite. If you have a positive 1, you move to the left. If you have a negative 1, you move to the right. So that made us happy. Here we go. Right? But what have we learned in this class so far? Yeah, whoever that was, I think I picked up the general feeling that it's not going to be that nice, right? Because I can just give you a quadratic function. Here's an example. I'm just going to throw this function at you. F of x equals x squared minus 2x plus 7. So it just looks like a very nice quadratic, right? We know it's going to be a parabola. We also know it's going to produce a minimum value. It's going to be a normal parabola, opens up, but we have no idea where it shifts, so we do not know the vertex, the way it's written, okay? You with me right now, right? We cannot answer that question, where is that minimum value? But we have done something like that before. We've looked at the expressions that have a square term and then just an x, and somehow we can turn it into expression that looks like that, where you have all the variables packed inside the square and nothing else matters. And we've struggled with that on Wednesday, I believe. And we've done that during the week 1 of the class. And I've told you that it will come back, and will keep coming back in this class. This little technique that now you probably already know what I'm talking about. What am I talking about? No. So how do we do that? When you have a square term and not a square term, and you all want to pack it together so you just have one big square. Complete the square. Yeah, that's what we tried on Wednesday. Remember, solving equations by completing the square. Now, the problem here, we need to alter our technique a little bit. Because before, we find a missing piece and we add it to both sides of the equation and then we keep solving. Well, you do not have both sides of the equation here. It's not an equation, it's a definitional function, f equals blah. There's no other side of an equation to add stuff to keep things balanced. But we can, we'll figure out how to deal with that. But first, we'll have to complete the square. That's what we'll have to do. Complete the square. So since we just did that last week, let's see how we can do that. So we have x squared minus 2x, and I'm not going to worry about that positive 7 for now. And my question to you is, just focus on the first two terms. Do you remember how to find that missing piece that we need to add in order to make that a perfect square from Wednesday's class? Yeah, so we're going to take the coefficient in front of x, we're going to divide it by 2, and we're going to square it. So we take the 2 in front of x, we divide it by 2, and we are squaring it. So this gives me that missing piece that I need in order to complete the square. So what am I adding here? What is this? So I have to add 1, right? Is that okay? So my incomplete square was missing 1. Before, when we had equations, we would be adding 1 to both sides of the equation to keep things balanced. Remember that? Well, we don't have another side of the equation to add 1 to. So what you have to do here, if you're going to add 1, you're also going to have to subtract 1 at the same time. It's kind of fun. So in reality, I'm just adding a 0 to my function. So I'm not changing my function. But the way I'm looking at it, the first 3 terms, x squared minus 2x plus 1, form a perfect square. The first 3 terms are going to factor into x minus 1 squared, because I have that plus 1. Now the last 2 terms, I can combine them. It's just, what is that? Negative 1 plus 7. Well, that's just 6. Now this is the same as my original function. If I open up the parentheses and combine like terms, I'll get the same exact expression. So here's the trick. Instead of adding 1 to both sides of the equation, since I don't have the other side of the equation, I'm going to add and subtract 1 on the same side at the same time, which is perfectly legal. Because we only have 2 legal steps in algebra that do not change the expression. It's multiplying by 1 and adding 0. This is adding 0. Because we just added 0, really. 1 minus 1. Did that make sense? A little mathematical trick-or-treat. But we can do that. Okay? Now, by completing the square, we got this result. And we can clearly see the vertex now, right? What is the vertex? 1 and 6. And this will give me the minimum, right? Because the parabola opens up. Wasn't that fun? So the only difference between this technique and the one we used with equations is that we don't have the other side of the equation to add to. So we have to pile everything on the same side. Add and then subtract the same amount. So make sure you're not changing your original problem. I'm going to do another one. So here's another example. G of x equals x squared plus 6x minus 11. So again, I'm not quite sure where the vertex is. So in order to find the vertex, I have to put it in that pretty form, the one that I like, that will clearly tell me where the parabola shifts. Therefore, it tells me where the vertex is. So we can do that again by completing the square. So I'm going to look at the first two terms. I don't care about that negative 11 for now. All I'm going to do now is to figure out what's missing from the perfect square. And the way we do that, we take the coefficient in front of x, which is 6, we half it, and we square it. So what do I need to add? 9. But if I add 9, subtract 9. So that means I haven't changed the problem. It's still the same exact problem. But now, the first three terms, x squared plus 6x plus 9, factor into x plus 3 quantity squared. So these are the first three terms. While negative 9 and negative 11 just give me negative 20. So this is the function. F of x equals x plus 3 quantity squared minus 20. And that's it. What is the vertex? Right, negative 3, negative 20. And again, that is the minimum value. So the function obtains the minimum value of negative 20 when x equals negative 3. So negative 20 is the minimum value when x equals negative 3. Is that okay? Are you happy now again? We're back to being happy? All right, well, let me fix that. Now, we know it's easy to complete the square when there is no coefficient in front of x squared. If there's no coefficient in front of x squared, that's when we start taking that term in front of x, dividing it by 2 and squaring it. But if I put a coefficient in front of x squared, in this example right here, negative 3x squared minus 12x plus 1. So now I have something in front of the x squared. Okay? So now if you go back in your notes, I think from Wednesday, and if you look at the steps when we were solving equations by completing the square, the first step was to just group all the variables on one side and all the constants on the other side. But then there was a second step that was telling you how to deal with the coefficient in front of the x squared. Does anybody remember that maybe? Maybe it's in your notes if you took some. Well, that's what you would do in the middle if you don't have a coefficient in front of x squared. But how do you get rid of that coefficient? Yeah, so we were dividing both sides of the equation, in this case by negative 3. But the problem, we do not have the other side of the equation to divide by negative 3. Okay? So the way out of that would be to factor negative 3 just out of the first two terms. Because really, you're completing the square just on the variables. Don't worry about that plus 1 for now. So I'm going to pull out the negative 3 out of the first two terms, which leaves me with x squared plus 4x. And I'm going to leave some room, and then plus 1. And then I'm just going to focus on x squared plus 4x. And I'm just going to complete the square inside those parentheses. Okay. Because again, we don't have the other side of the equation to divide by, so we have to keep working on the same expression. So we factor out -3 out of the first two terms. Then we're going to have to complete the square, and that's what we're going to divide by 2. We're going to take the term in front of x, divide by 2, and square that. So what do I have to add? 4. Okay? But in order to make everything back to normal, I have to subtract 4, but on the inside of those parentheses. And it's very important that you add and subtract on the inside because of that -3. Because when you added 4, remember, when you added 4 on the inside, that 4 is still being multiplied by -3. So you really subtracted 12. Because -3 times 4 is -12. But -3 times -4 is +12. So it still keeps it balanced. -12, +12. So make sure you add and subtract on the same inside those parentheses. So now we do have those 3 terms. That is a perfect square. So I'm going to take my time here. I'm going to write a few extra steps. -3 times first 3 terms give me x plus 2 quantity squared. Then I still have -4 and then +1. So again, I'm keeping track of that -3 and -4. I want to make sure that -3 multiplies -4. And it does in this case. When you distribute -3, you end up with -3 times x plus 2 squared plus 12 plus 1. So in the end, f of x equals -3 times x plus 2 squared plus 13. And -3, I want to make sure I understand that, -3 does not affect location of the vertex at all. It has nothing to do with the vertex. The only things that, yeah, the sign of the 3 just tells us whether it's minimum or maximum, but all we see that the vertex is at -2, +13, and that actually gives us a maximum because it's an upside down parabola. Does that make sense? So instead of dividing both sides by -3, since I don't have the other side to divide, I'm going to have to factor -3 and then really keep track of what I'm adding. And it's if you just take it as a rule, if you add something inside the parentheses, then subtract the same thing on the inside of the parentheses, you won't make any mistakes. It'll still be the same problem. And again, if you open up all the parentheses and combine like terms, you'll get the original question.
So you multiply that -3 up front, so you get
What was that?
-3 up front, you multiply that back to -4.
Well, I multiplied back to -4, and I multiplied it to that expression as well. So that's why I have -3 in front of the parentheses, and -3 and -4 gave me +12. So you still use your distributive property. You know, still applies. So how is that? Is that good? This is hard. This way to complete the square where you don't have another side of the equation and you have to keep track of all those extra constants that we were just ignoring before, we're just dividing things out. It's a little trickier. Okay? Any questions on this example? Make sense? Good. Good. Well, there's another way to find the vertex of a quadratic function. I'm about to teach you that, and you're going to like that method. Maybe a little bit better than that. So let's talk about this. So another way of finding the vertex. Of a quadratic function. So let's say I have, this graph. This is what we did with another class. One way to think about this, let's say I'm gonna do the following. I'm gonna pick up this marker, and I'm holding a black marker for those of you who don't see me right now. And then I'm gonna toss it up in the air like that. And it goes up and it comes down, right? So now picture the path of the marker and then that little graph that I drew on the board. Do they kind of look the same? Yeah. Well, close enough. They have the same pattern. So we both, we got the upside down parabola. But now I can ask you a question. Let's say, did that marker reach a height of 4 feet off the ground, above the ground? What do you think? Was that marker at any point flying 4 feet above the ground? How many times was it at 4 feet above the ground? Twice, right? If this was, let's say, 4 feet, and by the way, this graph represents me throwing it off the ground level, but that's all right. So 4 feet, we reach that height twice, right? On the way up and on the way down. And I'm going to label my horizontal axis as time and my vertical axis as position. So we usually like to use letter S for position. So here we go, position at time t. So I can ask you that question. Did we reach a height 4 feet above the ground, and how many times? You told me twice. I'm happy with that. Now let me ask you this question. Did we reach the height of 20 feet above the ground? No, right? The ceiling, how tall is the ceiling here? 10 feet, so yeah, So if this is 20 feet, so that marker never reached the height of 20 feet, right? So the 4 feet will reach twice, 20 feet will reach never. But then there is this highest point on the path of the marker. How many times did we reach that point? Once. So this is our maximum height, and the maximum height, let's label this T sub m for maximum, was obtained exactly once. Is that okay? Now, think back to what we did at the very end of Wednesday's lecture from last week. We were talking about quadratic equations, and sometimes they have 2 real solutions, sometimes they have no real solutions, and sometimes they have exactly 1 real solution. Remember that? That happened at the very end of the class. And there's a way to predict, without solving an equation, how many solutions it has. And it had a lot to do with the expression under the square root in the quadratic formula. We'll call it the discriminant. We did that at the end of Wednesday's lecture. The discriminant is d equals b squared minus 4ac, is the expression under the square root in the quadratic formula. And we agreed, and it should be in your Wednesday's notes, or if you pull it up off canvas, if d is positive, then we have 2 real solutions. So we reach the height twice. If I take this function and I set it equal to 4, I'll get 2 solutions. So the discriminant is positive there. If the discriminant is 0, then we have 1 real solution. So that's that maximum height. If I take my function, set it equal to the maximum, I'll get only 1 solution. And if d is negative, so you end up with a negative under the square root, so you get no real solution. You have a bunch of solutions with i's in them, but no real solutions. So since we're looking for the vertex, we're looking for the maximum point, which of those 3 statements about the discriminant we probably should focus on? Yeah, when d equals 0, right? This is what we like. Well, let me ask you this question. In the quadratic formula, if d equals 0, what do you have left? If d equals 0, yeah, but if d equals 0, then x equals negative b over 2a, right? So that square root goes away. You're left with negative b over 2a. Well, that's always going to be the x value of the vertex, negative b over 2a. That's simple. Okay? So this value negative b over 2a will always give me the x location of the vertex of the parabola. It will tell me where it's located along the x-axis. Now, if you know the x value, how can you find the y value? You know the function, you know the x value. In order to find the y value, you just plug it into your function. Okay? So this is the alternative way of finding the vertex. So the vertex can be computed by just doing negative b over 2a and then plugging it into your function. Isn't that nice? It's really easy to remember. It's whatever's left out of the quadratic formula when you get rid of the square root. And it's a lot faster than completing the square. But if I do a problem from before, the last example that we did, f of x equals negative 3x squared minus 12x plus 1, and we did that one by completing the square, I can use this vertex formula really fast. Because check this out. The x value, negative b over 2a, so it's negative of negative 12 divided by 2 times negative 3, right? Negative b over 2a, which is positive 12 over negative 6, which is negative 2. Okay? And that's exactly what we got for the x location of the vertex after we completed the square. Now the y value, I'll just have to compute my function at negative 2. So that is negative 3 times negative 2 squared minus 12 times negative 2 plus 1. So plug in that value into your function to get the y value. So that's negative 3 times 4 plus 24 plus 1. So negative 12 plus 25, so 13. Okay? So the vertex is negative 2, 13, which is exactly what we got before, right? Negative 2, 13. We got that same result by completing the square. Well, now we just use that formula. Negative b over 2a for the x, and then plug that x into your function to get the y value. How's that? Is that nice? Well, now I can make my function really, really ugly. Well, not really ugly, but something like that. 1/3, throw some fractions in there, minus 2x plus 2/3. Now, completing the square on that would be a little messy. But in order to find the vertex of that function, again, I'll just have to do negative b over 2a and take that result, plug it into the function. So negative b, so it's negative of negative 2 over 2a, so it's 2 times 1/3, right? So it's negative b over 2a, which is positive 2 divided by 2/3, right? 2 times 1/3 is 2/3. So this is 2 times 3/2. 2's cancel, equals 3. So that's the x location of our vertex for that function. Well, if I do this problem, so the question was the discriminant has to be 0. Now, it will be 0 in this sense. If I set this equation equals maximum value, whatever the maximum value is, which I don't know, and if I solve that equation, discriminant will come out to be 0. Okay? Now, this equation, I mean, this function as it's written, the discriminant there doesn't quite make sense because we're not looking at the equation. But we use that discriminant with that prior knowledge that that's the only time when you get one solution is when discriminant is 0. So we kind of backdoored our way to that negative b over 2a. So x is 3. To find the y, we plug 3 into our function. So there you have to compute. It gets a little bit messy, but it is 1/3 times 3 squared minus 2 times 3 plus 2/3. Okay? So 1/3 times 3 squared, one of the 3's cancel, so that's just 3 minus 6 plus 2/3. So this is negative 3 plus 2/3, which is negative 2 and 1/3. Right? So this is the vertex of this parabola, 3 and negative 2 and 1/3. So that would be the minimum value, negative 2 and 1/3. How is that? Is that good? It's a little easier than completing the square, right? But now we can do some of those maximization, minimization problems without using the calculator. Do you remember the problem we did with the farmer and the cows and the river? Remember that? I told you the joke you didn't get. Remember that day? Yeah. So like I don't remember the problem exactly. We kind of recreated with another class, with the other class, and it's not quite the same. But let's say we're going to build a fence like that, and we decided to split it into 3 regions, and these are all x's, x, 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 and we decided that we have 3,200 feet of fencing. So I want to find the dimensions. The value for x will produce the maximum area. And we realize the area of the total thing is just length times width. So if we label that side as y, the area is simply x times y. Right? Length times width. Now the problem with that, we have 2 variables, x and y both unknown. So we have to find a way to express y in terms of x. Right? And when we did that, because we remember we have 3,200 feet of fencing, so that means x plus x plus x plus x plus y has to equal 3,200, right? So it's 4x plus y equals 3,200. So you can solve for y. Y equals 3,200 minus 4x. We can take this expression and we can substitute it in for y. So if we do that, that will give me a function of x. A of x equals x times 3,200 minus 4x, which is negative 4x squared plus 3,200 times x. Okay? Is that all right? That's a quadratic function, has a negative in front of x squared, therefore it has a maximum. So now we can find that maximum by doing our vertex. So in order to find the value for x that will give me the maximum area, I just have to find the vertex. So x equals negative b over 2a. So this is negative 3,200 over 2 times negative 4. Negatives cancel. We end up with 3,200 over 8, which is what, 400? 400 feet. So x has to be 400 feet. Isn't that nice? Do you understand the leap in our abilities that just happened? That we can find that location without looking at any graphs, without plugging any things in the calculators. We can just do that little formula and we can find a point that will produce the maximum area. Yeah, it's very exciting, isn't it? Now the value of that area, actually to know what is the maximum area, we'll just plug in 400 back into our function. And it's probably easier to plug it in when it's factored. So it is 400 times 3200 minus 4 times 400. Is that right? So that is 400 times. Now this is 1600, so times 1600. 4 times 16 is 64, followed by 4 zeros. So 640,000 square feet. That is this is the maximum area possible in that scenario. And it'll happen when x equals 400. And we did build a fence along the river. Yeah? That's exciting. So that's the good news. If a function is quadratic, we can do that. The bad news, if the function is cubic or anything higher than that, we cannot do that yet. But we'll be able to one day to find those fancy points regardless of what a function is. But not now. Now we can only do it with a quadratic. So questions on this example? Really? No questions? It made sense? Good. Let's do another one. So remember I was throwing that marker? You see I have two of them over there, by the way. I threw red one with the earlier class. Now it's, yeah. Look at the group I get there. See the consistency of my marker throw? They're just like dead on. People online have no idea what I'm talking about. They're next to each other. It's a good day for me. All right. Well, on planet Earth, when I throw a marker like that, it actually follows a very specific set of rules when it flies through the air and falls back on the ground. So on planet Earth, the height in feet of a free falling object at time t, where t is measured in seconds, is given by this formula. S of t equals negative 16t squared plus v sub 0 t plus s sub 0. And I'll tell you in a second what v sub 0 and what s sub 0 are. Just write that formula down and I'll talk about it a little bit. You don't need to memorize this formula, by the way. It's just if you're required to do some proctored work where that formula is required, you'll have that formula. Okay, you just need to know what it is. It's just that. But v sub 0 or v naught, that's the initial velocity. And s naught, that's the initial height, initial position. Is that right? The high spell height? So in my problem, the one when I was throwing the marker, we can actually say that I kind of went from what, like a knee level or something like that, or maybe hip level. What was it, like 3 feet above the ground? So that was my initial position. Can you predict how fast I threw it to begin with? What was the initial velocity when it went flying? The other group was very generous, gave me 15 feet per second, which I doubt. It went that fast. But we can just go with that, so then, because then all the math, I don't have to, all the math has been figured out already. But it doesn't matter. I'm still going to pull out the calculator, because now things going to come out ugly. The number's not going to work out in any pretty way, because we're trying to do a more realistic question. So we can do whatever you like. So initial height was 3 feet. That's kind of okay. What do you think the initial velocity was when I threw that marker? 2 feet per second. Nah. Let's go 100. I launched it out of some kind of a device. Because then it flies longer. It's more fun. Otherwise, I'm working with like a quarter of a second time span. It's going to be hard. Let's do 100 feet per second so it flies a little further. Or maybe not. I don't know. Okay. So if that's given to us, that we started with 3 feet above the ground, and it went originally at 100 feet per second, then our position at time t is given by negative 16t squared plus 100t plus 3. So yeah, we're going to get different numbers. Oh, that's just planet Earth. That's our gravitational thing. If we were on other planet, it would be something else. Okay, so negative 16, that's your, well, actually it's 32. It's the 32 feet per second squared. That's your acceleration on planet Earth. It just needs to be 16 in this case. If we were in meters, instead of negative 16, we would have negative 4.9 if we were in meters. But since we decided to do feet, it's negative 16. So that's just given. That's fixed. Okay? All right. Well, I can now start asking you certain questions. Find the height of the marker after 2 seconds. So I let it go, and 2 seconds later, I want to know how high it is above the ground. With another group, we actually ended up with a negative number, which means after 2 seconds, it's not flying anymore. It's been on the ground for a while. If the marker could go through the ground, we actually ended up with like 31 feet below the ground with the previous one. But if you go 100 feet per second to begin with, we might get something nice. But anyways, since this function tells us, the job of this function is to tell us the height of an object at time t, and I'm giving you time t, so all we have to do is just plug in 2 into that function and see what you get. All right? So all we have to do is to evaluate s of 2. So that would be negative 16 times 2 squared plus 100 times 2 plus 3. Okay? So it's negative 16 times 4 plus 200 plus 3. So what is that? Negative 64 plus 203. So what are we getting? 139, you said? I know, 139. I said 139. I don't know what I say. I have, yeah. So if I actually managed to give it the initial velocity of 100 feet per second, that's what would have happened. So after 2 seconds, it's 139 feet above the ground. Okay? Isn't that cool? Yeah. I can ask you this question now. When will the marker reach the height of, let's say, 50 feet? Right? That would be interesting. So how long it takes for the marker to reach 50 feet? And most likely it will reach 50 feet twice, on the way up and on the way down. And we're going to start solving our equation. We might get 2 solutions. And one of them will present how long it takes to get to 50 feet on the way up, and the other one, how long it takes to get to 50 feet on the way down. But all it says that your height is 50 feet. So we need to solve this equation. Our function equals 50. So negative 16t squared plus 100t plus 3 equals 50. Right? That is a quadratic equation. We shouldn't have any problems solving that quadratic equation. So in order to solve a quadratic equation, move everything to one side. So negative 16t squared plus 100t minus 47 equals 0. Right? Subtract 50 from both sides. Now, since we have a negative up front, it's always a little awkward to solve quadratic equations when they start with a negative. It's a little messy. So just a general suggestion, every time you're trying to use the quadratic formula, because that's what we're about to do, and your function has a negative sign, just multiply by -1. Change all the signs. It will just be easier. So it's 16t squared minus 100t plus 47 equals 0. Because now it's an equation, so we can mess with that. All right, well now, I don't think we'll be able to factor this very much. It's just messy. I'm not even going to bother trying. I'm just going to plug it in the quadratic formula. And this is, again, the general rule. If it takes you more than 12 seconds to factor, then don't. Just plug it into quadratic formula. So negative b, negative of negative 100, plus or minus the square root of b squared minus 4 times a times c all over 2a. Right? Quadratic formula. That's going to be, I probably need to calculate. So 10,000 minus, where's our calculator? So 4 times 16 times 47. So minus 3,008 all over 32, right? So numbers are getting pretty ugly. So what is this? 6992 over 32. Oh. Yeah? Hey, ugly numbers. What can you do? Now, 6992 is probably not a perfect square. And it's not, what is it divisible by? Can I simplify this? Or should I just, oh, even better. Looks like 6992 is 16 times 437. That's what I just discovered by accident, just by creative division. And 16 is a perfect square, right? So that makes my life a little bit easier. So this is 100 plus or minus, take the square root of 16, which is 4, square root of 437. I'm not going to mess with 437. It feels like a prime. Does it? Does it feel like a prime number to you? No? Yeah, but so what? Yeah. But it's very hard to identify prime numbers. You know that? It's really hard to recognize a prime number. Or maybe it's not. I don't know. I don't know. I'm not making any claims about it, but it looks like it doesn't have any perfect squares in it. That's what I'm pretty sure about. Or maybe, I don't know. Well, it's not divisible by 3, definitely not 4, not 5, not 6, not, well, 7, I have no idea. Maybe divisible by 7, who cares? If it is divisible by 7. Yeah. Do you know, right? Prime numbers, they're really hard. If I give you a prime number that's long, it's hard to identify. That's why your internet security almost works, because it's based on our ability to recognize large prime numbers. They have competition. You find a prime, if you discover a new prime number, they might give you a prize. But it has, many, many digits. Yeah. Sorry. So everything is a multiple of 4. I can reduce everything by 4 just to make our computation a little bit easier. If I reduce everything by 4, we'll end up with that. 25 plus or minus square root of 437 over 8. Okay? So that gave us 2 points in time. I can plug them in. T equals 437 square root plus 25 is that divided by 8. So 5.74-ish. So that's 1. And the other one was, if we use the minus, 437, take the square root, subtract that from 25. Okay, I made a mistake here. 25 minus square root of that, divided by 8, so about half a second, 0.51. So that's how long it took us to reach 50 feet on the way up and on the way down. Isn't that exciting? Do you want a break? Or we keep going? Yeah? All right, let's do a break, and then we'll continue. Okay, so we were playing with this function. We still can answer a few more questions about it. So here's another question. So that's probably question C. How long does it take for the marker to hit the ground? Okay? Because it did land on the ground, so the question is, how long did it take? And again, we do know that the height at any given time for this specific example was given by this function. So, how do we go about solving that? So it hit the ground. Set it to 0, right? So set s of t to 0 and solve for t, because the height is 0 at that time. So negative 16t squared plus 100t plus 3 equals 0. Which is a quadratic equation. We're just going to use the quadratic formula. We're probably going to get 2 results. One of them is going to be negative. And the reason for that, because I started with 3 feet above the ground. Okay? So it will actually kind of give me, if I started from the ground, kind of going back in time a little part. So we're just going to ignore that negative result, because it's only going to be on the ground once when it lands. But anyways, so t equals, using the quadratic formula, negative 100 plus or minus the square root of 100 squared minus 4 times negative 16 times 3 over 2 times negative 16. So just computing that, it's 10,000, and then what's going on over there? It's 64 times 3, 192, so plus 192 over negative 32. And again, I can reduce this radical as 10,192 is divisible by 4. I don't know whether it's divisible by 16. But really, we're just going to end up plugging it in the calculator anyways. Yeah, it is. I can simplify it further. So 637. 10,192 equals 16 times 637. So again, taking the square roots gives me that. And I can reduce everything by 4 again. So that's gone, that's 25, and that's negative 8. Technically, you cannot because of the middle part. But since the middle is plus or minus, you can actually go ahead and reduce everything by negative. It's actually going to give you 25, well, minus or plus. So it's still plus or minus square root of 637 over 8. Yeah, that wouldn't matter. So just plug them in the calculator. One's going to be positive. One's going to be negative. So here's the positive one. Square root of that plus 25 over, wrong number, over, all right, messed it up. 637, the square root of that, plus 25 equals that, divided by 8, so about 6.28 seconds. So that's how long will it take to hit the ground. If I do the minus version, it'll give me a very small negative result. 25 minus the square root of 637. So you see that's already negative. And if I divide it by 8, so it's negative 0.03 of a second. So that answer, we cannot use that answer. So this is how long it took for the marker to hit the ground, assuming I threw it at 100 feet per second. Is that okay? By the way, we haven't used anything new that we learned today about the vertex, but I can ask you now, find the maximum height. Reached by that marker, and that will be finding the vertex. Okay? In order to find the maximum height, we have to do the vertex formula. So t would be negative b, so it's negative 100 over 2a, so it's 2 times negative 16. So it is 100 over 32. Negatives cancel. And I can again reduce everything by 4, so it's 25 over 8, or 3 1/8 of a second. So that's how long it took to get to that highest point. Okay? To actually find that highest point, I need to plug that number back into the function. So it's negative 16 times 25 over 8 squared plus 100 times 25 over 8 plus 3. So that will actually tell me what the value of that highest point. So here we go. So 25 over 8 is that squared times negative 16 gives me that much. So as the first term, I'm going to store it in my little memory thingy. And then I have 25 over 8 times 100. I'm going to add that to my memory. Ooh, let's hit the wrong button. 25 over 8 times 100. Add that. And then 3 add that. So 159.25 feet. So that's the highest point on the path of that marker. So the maximum height is 159.25 feet. Okay, how's that? Make sense? All right, good. So that's section 3.3. Now 3.4 focuses on two types of equations. Equations that involve radicals and equations that involve algebraic fractions or rational expressions. We'll just do radicals today, and then we'll do the rest on Wednesday. So section 3.4, we will start with solving equations that involve radicals. Okay? So let me give you a very simple equation. Here's an equation, here's an example of an equation that involves a radical, which means some kind of a root, whether it's a square root or a cube root, whatever. Those are all radicals. Would you be able to solve this equation? What do you think? How would you do that? Square both sides, kill that radical, right? Square root feels like we should square that, and you're absolutely right. We're going to go ahead and square both sides, and that will give us a solution, x equals 4. Is that good? Well, that's right. Looks like it's going to work. If I take 4, plug it back into the original problem, that works. What if I give you this example? Cube root of x equals 2. Can you solve that one? What? What was that? Yeah, cube both sides. Feels like we should get rid of that cube root. So if I cube both sides, we should be good. So x equals 8. Is that okay? So that's really going to be the message when solving equations that involve radicals. It's just going to be about getting rid of those radicals. Okay? But there is a little problem. And don't write this down. I'm going to give you the easiest equation of this semester, of your life. This is the easiest equation. No equation is easier than this one. X equals 1. Can you solve that equation? What is the solution to that equation? 1, right? There's nothing else that solves that equation. Do you all agree with that? This equation has exactly one solution, x equals 1. But let me show you what happens if I just all of a sudden walk over and square both sides. Right? So I get x squared equals 1. Well, what are the solutions to this equation? Yeah, plus or minus 1. Now, positive 1 still works in my original equation, while negative 1 does not. So when you square both sides of an equation, sometimes it produces this what we call extraneous solutions. You go through this lengthy process of solving an equation, and your math is perfect. You haven't made a single error, and you get an answer, and that answer is just wrong. It just doesn't work. So in this type of situations, we always have to go back and actually check our solutions to make sure that we don't get any extraneous ones. Okay? So this right there is called an extraneous solution. And we don't like them because they don't solve the original problem. And that happens when you square both sides of the equation. And it's really hard to predict whether you're going to get them or not. And sometimes you get 2 solutions and none of them work. Sometimes you get 2 solutions and both of them work. Sometimes you get 2 solutions and only one of them work. So there's no way to know but to actually check. Especially when you're squaring both sides. When you're cubing both sides, you don't have to. It's not going to happen. Only with even powers. Because the even powers start ignoring the negatives. They make other ones work as well. So, but here are the steps. I'm going to outline the steps in solving equations that involve radicals. So here are the steps. Solving equations that involve radicals. So step 1 is to isolate a radical. Okay? You just want to get a radical on one side of the equation and don't care what's on the other side of the equation. So first step is to isolate the radical. So square root or cube root just by itself on one side of the equation. Now the second step would be to kill that radical. And the way you kill that radical is by either squaring it or cubing it or whatever. If you had a square root, then you square both sides. If you had a cube root, you cube both sides. If you had a fifth root, you raise both sides to the power of 5. So you're going to raise both sides of the equation to whatever the index of the radical is. So we're going to raise both sides of the equation to the index of that radical. So again, the square root, square both sides, cube root, cube both sides, and so forth. Now, the third step, after you do steps 1 and 2, there still might be radicals left, because you might have started more than one. So check for more radicals. If there are still radicals left, then repeat steps 1 through 3. Go back, isolate and kill. So whatever you see as a radical, isolate it again and kill it till all the radicals go away. If there are no radicals left, move on to step 4. And step 4, after you do all that, you get rid of all the radicals, you'll have a nice equation, nice polynomial equation. So solve the whatever equation you have. It doesn't have any radicals, by whatever means possible. And step 5 is to check your solutions for extraneous. So this is the process. But really, the big thing here is to isolate and kill, till all the radicals go away, and to check your solutions. So let me do a few examples. A square root of 2x minus 1 equals 3. So all we have is just a single square root on one side of the equation and a constant on the other side. So the radical is already isolated, so I can go ahead and kill it. And I'll do that by squaring both sides of this equation. So if I square both sides, it gets rid of the radical on the left. So the left-hand side is just 2x minus 1. And the right-hand side now is 9. Okay? So no radicals left. Now I can just solve that equation, right? Should be pretty easy. To solve this equation, add 1 to both sides. 2x equals 10. Then divide by 2. X equals 5. Are we done? I have to check. So this is how we check. It has to satisfy the first original equation. So this is checking. So if x equals 5, we'll plug it into our equation. So square root of 2 times 5 minus 1, will that equal to 3? What do you think? So this is a square root of 9. That does equal 3, so that checks out. So that's our solution. Okay? In this case, the checking process went pretty fast. I'll have a problem down the road. That was just an unfortunate accident. The solution come out extremely ugly. So checking is just, you just plug it in a calculator because they're just, your head will explode if you try to drag those numbers through. Yeah, but is that okay? Good. Here's another example. Square root of x, square root of x plus 1 minus 2x equals 1. So we have a square root and another thing. So step 1 is to isolate the radical. So we will add 2x to both sides. So that's the step 1. So we have the square root of x plus 1 equals 2x plus 1. So now we're going to square both sides to kill the radical. So the left-hand side is simply x plus 1. So square gets rid of the square root. While on the right, I have to square a sum. So you can either FOIL, write it 2x plus 1, 2x plus 1. Or you can use a formula that tells you how to square a sum. In either case, you should end up with a 4x squared plus the double product, which is 4x plus 1. So there's the double product in the middle. That's why we divide by 2 and we complete the square. But middle thing is always a double. Okay. So there are no radicals left, right? So I can solve that equation. It's just a quadratic equation. So subtract x, subtract 1, subtract x, subtract 1. So we'll end up with 4x squared plus 3x equals 0. Okay? That is a quadratic equation. We can solve that one by factoring. You can just pull out an x. That leaves you with 4x plus 3 equals 0. So it's either x equals 0 or 4x plus 3 equals 0. So x equals 0, we're done. 4x plus 3, x is negative 3/4. Right, subtract 3, divide by 4. So we got two solutions. We still need to check both of them. And again, you really have to check both of them. If first one works, doesn't mean that second one doesn't. Or if the first one doesn't work, doesn't mean the second one doesn't work. And there is no way to predict just, if it's negative, maybe, there are no signs. Have to really check. So checking. So if I do x equals 0, I'll plug it back into the original equation, which was all the way up here. So I'll get square root of 0 plus 1 minus 2 times 0. Will that equal to 1? Yes, right? I have a square root of 1 equals 1, so check. So x equals 0 works. Okay? We also have to check the other one. X equals negative 3/4. If I plug that one into the original equation, we'll end up with a square root of negative 3/4 plus 1 minus 2 times negative 3/4. Will that equal to 1? This is a 3/4 here. So negative 3/4 plus 1 is just square root of 1/4. Is that okay? Negative 3/4 plus 1 is just 1/4. Two negatives give me a positive. 2 and 4 reduce to 3/2, so it's plus 3/2. Now, will that equal to 1? I don't need to continue because I know that 3/2 is bigger than 1, right? And I'm adding something to it, so it's even bigger than 1. So it's not equal to 1. And if I actually continue working the left side turns out to be 2. It's 1/2 plus 3/2. And 2 is clearly not equal to 1. So this solution is extraneous. So x equals negative 3/4. There's the extraneous solution. So the only solution is x equals 0. Okay? So when you're going to be working on these types of problems on that math lab thing, it's really important that you check your answers because it doesn't like the extraneous solution. It might ask, which ones are extraneous, things like that. So keep in mind to check every time. Okay, so only one solution works. How you doing so far? Good? Isolate and kill, isolate and kill. That's what we're doing. All right, now let's do the really messy one. Square root of x plus another square root under the first square root, like that. It just happen like that. You have a square root inside of the square root. Equals 4. And that 4, it was an unfortunate choice of a number earlier today. That's what we're going to get us out of hand really fast. I wish I put like at least a 2 in there or something. But hey, I made the other group cry, so I'm going to make you cry. But all I see is one big square root on the left and 4 on the right. I don't care what's under the square root. All I see is a single square root. So I'm going to kill it. I'm going to square both sides. So that will get rid of the most outer square root. That square root goes away. So that means the left-hand side now is x plus square root of 2x plus 1 equals 16. So I just killed that most outer square root, and I just copied the radical. Is that okay? So with step 1, 2, step 3, check for more radicals. Yeah, there is still a radical left. So go back to step 1 to isolate that radical. So I need to isolate the square root of 2x plus 1, so I'm going to subtract x from both sides. So that leaves me with the square root of 2x plus 1 equals 16 minus x. Is that okay? And now square both sides again, because we'll have an isolated radical. Square both sides, square both sides. So on the left, we just have 2x plus 1. While on the right, 16 squared is 256 minus the double product, that's 32, plus x squared. So that 256 is just exploded on us there. It's the product of 16 and x and 2. Because that's how you square things. When in doubt, FOIL, right? 16 minus x, 16 minus x. At some point, you're going to have negative 16x and negative 16x. So if I move everything to one side, I'll get x squared minus 34x plus 255 equals 0. Right? Subtract 2x from both sides. So that is a nasty quadratic. I don't think, well, you can factor that one. So we're going to use the quadratic formula to solve this. So x is negative b, so it's negative of negative 34 plus or minus the square root of negative 34 squared minus, right, what is it? Minus 4 times 1 times 255 all over 2 times 1. Right, the quadratic formula. So negative of negative is positive. So 34 plus or minus the square root, and you're going to need a calculator on this one. So 34 squared, so it's 1156, minus 4 times 250 is 1,000, plus another 20 minus 1,020, all divided by 2. So this is 34 plus or minus the square root of 136 all over 2, right? Is that right? And 136 is 4 times I did make a mistake in the earlier session. I have to go back and fix that. So it's 4 times 34. No, it's not. Is it? Yes, it is. Yeah. So it's 34 plus or minus 2 square roots of 34. And what I did with another group, I just kept my square root as not 34 but 17. That's what I kept with a 17. Because now you reduce everything by 2. Yeah, maybe now it'll work. 17, oh, I need to fix that. 34. So we reduce everything by 2. Yeah, that's better. Well, I don't know whether that's better. Because earlier, none of our solutions worked. Because, well, came out wrong. But I'm not saying that any of those will work. But that's 2 solutions. Right? Am I correct here? Yeah, I don't know how did that happen. Oh, just being stupid. Okay. Well, I need to check that. That's just ugly. I have to take whatever this answer is and plug it all the way back into the most original version of my question. Are you ready for that? There's going to be some handy calculator work. Okay. So let me do the plus. 34 square root of that. Okay, let me first clear my memory here. So 34 square root of that plus 17. So this is just the x value. So I'm plugging it in here, so it's times 2 plus 1. And then I'm going to take square root of that, so it's 6.83 or whatever. I just computed the little square root. But then it says add the original problem to it, so it's plus 17 plus square root of 34 equals that. Took square root of that, so 5.44, which is not the same as 4, right? I know I went through that fast, but it's just, I'm plugging in that answer. Okay. It might still not work, so it's not that big of a deal. Now if I do the minus, 17 minus square root of 34 is that, times 2 is that, plus 1 is that. Take the square root of that, you get that. So that's just the little radical. Then plus x, which is 17 minus the square root of 34. Son of a bitch, that works. Because now I'm going to take square root of that, and that's 4. So one of them works. 17 minus square root of 34 works. Oh boy. Can't believe that. Yeah. Well, no, it's just sad that I did that. See, this is why it's good. You see, I used those notes from the last class just to write the original question, but I don't look at it again, because But anyway, so 17 minus square root of 34 works, while x equals 17 minus square root of 34 is extraneous. Ooh. Thank you. See, you gotta look out for me. See, I had a feeling. That's why I didn't post that other video yet. I posted the notes. So I should take that. Good. All right. Because I was very surprised that none of them worked. Because that's totally fine. If none of them work, oh well, none of them work. Okay, good. But that kind of killed my mood for the rest of the class. But I only had one more problem left. So that was okay. So we have time for one more. All right. Here's another one. A square root of x plus a square root of x plus 1 equals 2. So I have 2 square roots. I still have to isolate one of them. Okay? I cannot just start squaring things, because it will, if I just square both sides, it will give me even messier square root. Because remember that double product in the middle. So I cannot just start squaring things. So I'm going to subtract square root of x from both sides to write it as square root of x plus 1 equals 2 minus the square root of x. So now the thing on the left is isolated. So I can kill that one. But I will still have another radical on the right after I do the squaring. But that's okay. It's a small radical. So the thing on the left is x plus 1. And the thing on the right, square first, that's 4, minus the double product. So it's 2 times the square root of x times 2. So that's 4 square roots of x plus square root of x squared. That's just x. So that's what happens when you square the right side. It still has a radical left, right? So I need to isolate and kill again. So subtract x from both sides, so they actually both cancel. Subtract 4 from both sides. We end up with -3 equals -4 square roots of x. Divide both sides by -4, you get square root of x equals 3/4. Okay? By the way, if your answer would come out square root of x equals -3/4, you can just stop, because square roots cannot be negative. Square root of x cannot equal -3/4. So always has to be positive on that side. So now again, kill that radical. Square both sides. X equals 9/16. Okay? I still need to check that. And when I check it, I plug it back into the most original problem. So here's checking. X equals 9/16. So when I plug it into my problem, I'll get square root of 9/16 plus the square root of 9/16 plus 1. Will that equal to 2? So square root of 9/16 is 3/4. While 9/16 plus 1, I have to turn 1 into 16 over 16 to get the common denominator. I'm going to turn 1 into 16 over 16. So 9 plus 16 is 25 over 16. Right? If you add 1, yeah, it'll work out. So 3/4 plus square root of that is 5/4, which is 8/4, which is 2. So that checks out. Okay? So the only solution that we got actually worked. Yeah. Good? Good stuff? All right. Well, good thing I was recording the second lecture. Usually if I had a feeling something was wrong. All right, so I'm going to stop this one. I will